right, so let's move on to improvements. We talked about the Aloha protocol, and it was wireless. We also talked about like ordering the packets to ensure that there wasn't small overlap. But let's talk about taking that to the next step, and let's move to a wired network and see what else we can do for improvement. So if we have three computers that are sitting on a network, right? And this network right now is just a single wire, right? We all connect to the single wire. So, and we want to be able for these to talk to each other, right? We can use the same idea in Aloha to simply say, hey, we're going to talk. So A, B, and C are on the network. C starts talking to A. And just like in the Aloha we talked last week, we're going to listen first, right? So if we listen first, is it possible for A to collide with C? Sure. Why? So you could do it instantaneously, right? Or you just magically pick the exact same time to do it. But we also have a delay that crosses this network, right? And so this delay, any time in that delay, any time at all, C could, if C was already transmitting, A could start talking and not think that anybody is talking, correct? So if C was sending a packet across here, right, and it was moving across, even if the packet had just started moving down here, it was on the point of reaching and talking to A, or hitting the line on A, it doesn't actually matter. It doesn't have to talk to A, right? Because everybody on this type of network hears everything, right? But just at this point, A can start transmitting, and the collision can happen right there. So it is possible, even though we're listening prior to doing this, because of the delay, we could have it. So, but we have advantages in a wired network, right? The advantages in a wired network is that if we hear a collision, or we can hear a collision where in a wireless network we can't hear a collision, right? Because if in a wireless network, if A started talking here, right, there's not any possible way that it could have heard the signal from C because it talks too loud. But in a wired network, we can do that, right? So we could hear the collision right here. And then, unfortunately, that packet is dead, right? Because we have jumbled the information in it because we started transmitting. But A could quit transmitting here, right? But we need to notify sometime notify C that, hey, we've had a collision, you're going to have to repeat. So, in this case, A could send out a signal that says, hey, there's been a collision. And we send that, it's called a jam signal. And we jam the network, right? And then after after D time, again, then everybody on the network would have been notified of the collision, right? So A hears it, then A can propagate out the network, and then D time again, everybody could be notified of the collision. So what is the maximum, if C was to be sending this packet, what's the maximum time that it would take for C to be notified of a collision? 2D. 2D. It can't be any possibly longer than 2D, right? So long as we have some kind of processing that's relatively fast, right? But 2D is generally the time that it takes for C, because the signal can leave C, make it just to A, right? Have the collision, and then A notifies, hey, there's a jam signal, so it takes all the way to get here. Now, if the collision happened near here, right? The collision happened near here, then B would get it in some time less than 2D, right? And then propagate out, right? But 2D is the max. So it turns out that this network kind of works well, so long as the frame is small. So if you read that in your book, I'm not sure it says that in the book, but it definitely says it in the supporting materials. It says that this is a good defense against collisions only when BD is small. So BD being the bandwidth delay. When they say that, what they really mean is that it's small relative to the packet size. Because we can have very large BDs. So in a 10 megabit network, right, because it's 10 megabit and the delay is over 100 meters, right, BD is fairly large. But what that really means is this works well so long as the packet is the width of the network. Actually, it would even be better if the packet was 2 times the width of the network. Why?
Because of the round trip.
Because of the round trip, because of this. Now, imagine C starts transmitting, and it transmits at 2 times, the packet length is 2 times the length of the network. Right? And so it starts putting stuff on the wire, right? And then right at half of the time it takes to transmit the packet, the collision happens, right? And then the jam signal comes across, and it will be notified right as it stops sending the last packet. There was nothing lost there, right? Had the packet been small, then we would have had this open network, empty network. So think of network in that sense as a storage medium, and it's now empty, right? If we make it 2 times the length, if we make the packet 2 times the length of the network, then C will be notified right at the time it quits sending anyway, and so it can start sending again. And so we start maximizing the bandwidth of the network. And this happens because you can hear the anything on the network can hear a collision. So if you go to early Ethernet, classic Ethernet, that I believe was 10 megabits per second. So classic Ethernet at 10 megabits per second, and because of the lengths, if you do all the math, you'll figure out that, hey, that packet needs to be at least 64 bytes long. So that means that every packet on classic Ethernet is 64 bytes, even if you're only sending 1 byte. Now it's hard to send 1 byte because we didn't talk about addressing and stuff, other stuff that we're going to put in there, right? But the minimum length becomes 64 bytes, and that is because we want the packet to be at least as the width, 2 times the width of the network. Now, if we increase that and went to 100 megabit per second network, right, then, and we kept the length the same, then our packets would have to get bigger. Right, because that being 100 megabits per second network with the same length simply means that it can put more signals on the wire faster. The frequency of putting signals on the wire becomes faster. So the packet length, even though the delay is the same length, the packet length gets longer relative to byte size because it still needs to fill the network, 2 times the network. So 2 times the bandwidth delay product becomes a very important concept in network. Because that is the time that it takes to be able to guarantee that you hear a jam signal on the collision detection network. So the problem with, okay, now let's say A, B, and C are on this network. We detected collision, and because we could detect a collision, C is able to transmit the packet across correctly. And so the moment we detect the collision, we transmit the packet across. Is there any problems now? Any hiccups that we might have? It's assuming that A and B stays quiet, but let's say we have an algorithm. Let's take care of that little problem. Say we have an algorithm. Hey, if there was a collision and C spoke first, or in this case C spoke first, C gets to transmit again. We can fix that. Is there still a problem? So let's say A and B both want to talk. Who gets to talk first? So the problem with it is that once there is a collision, you artificially put a boundary in the network, right? So there's a collision, there's a boundary, C gets to transmit its bytes, and then there's another following boundary, right? And now, if we don't do anything, everybody else in the network is going to try to talk at the same time. Anybody that wants to talk while all this collision and retransmission happened now gets to tries to talk at the same time. So what do we do to fix that?
Do a random offset.
We do a random offset, right?
By Mac or something.
Huh?
By Mac or something.
Sure, we could do it by Mac. Right? How else could we do it? Man, that would make some computers more equals than others, right? How else could we do it? And the Mac might be a problem. That means that that everybody has to know who else is on the network, no matter what. So even if you joined up, if we're just doing simple Macs, then now everybody needs to know the Mac, right? And so we're trying to design a distributed system that not everybody needs to know who's on the network. I would like to have a system where we can all sit in here, well, we're talking about wired network, but imagine here, I need to develop a system that everybody in here, some people will have Wi-Fi on, either in their laptops or in their pockets, whatever. I need to have a system that I don't need to know who else is on the network.
Classic Ether, I think, used tokens.
Nope, Classic Ether didn't use tokens.
Well, that's
Token.
token.
Yeah. So this is Classic Ethernet. This is Carrier Sense Multiple Access Collision Detection, right? CSMACD. So, but we can do a random. We can use that, but then we have a breakage distributed system. We can put an algorithm on this, like, okay, you get on network, you have to announce yourself. Right? We can do that, and then everybody builds tables, figures out who's in line. Anything else we could do?
Just a random number.
We could do a random number, but what random number? So in this case, if we were going to pick a number between 0 and what in this little tiny network, what would be the best number to pick?
Size of the packet, maybe, or delay.
The best number to pick turns out to be 3, or actually an offset, so 0 to 2. Because there are 3 on this network. If we had 100 on the network, the best number to pick, a random number to pick, would be 0 to 199. And that is times the packet length, the delay, right? The problem now is I just reintroduced his problem. Right? Now I don't need to know everybody's MAC, but I need to know how many people are on the network. Right? I just basically took a variation of his problem and said, hey, right, now we're going to do a random number. How do we choose the random number? So how do we fix that?
Just have a counter of how many more attached to the network.
But then everybody has to announce themselves again when they attach the network. We would like that when you attach the network, you don't have to announce yourself.
Is this where you get into coding?
Well, this is definitely an algorithm. So we're above the physical layer now, and we're deciding through either something coded in hardware or coded in software when to send the next packet. And I'm telling you that in the best case would be to be able to know the number of the network, the number of nodes on the network, and take the inverse of that number.
Yeah, that's what we used to.
So, but I don't want to know everything on the network. So what if I just took the best case scenario and said, well, there's at least 2 people on this network, right? There has to be at least 2, otherwise we're not talking, right? And so the first time I do it, I do 1 and 2. Right? So that creates a number between 0 and 1. And then I try. If I have a collision, what do I do?
1 and 3.
Huh? Well, it's close though.
1 and 4.
Huh?
Double it.
Yeah, we're gonna double it. Now we're gonna go, we're just gonna have, in a computer, this is just a shift, right? So we're just gonna shift left and double it. So now it becomes 0 to 3. If I have a collision again, 0 to 7. Have a collision again, 0 to 15. Now this is going to, how many times does it take to get above 100 nodes on a network? Huh? Right, so this is the default, right? So this is the first double, second, third, right? It only takes 6 times to get there. And now you can accommodate more than 100 on your network, and then depending on the implementation, you can de-escalate that number at some point, right? So, but the idea is how do we vary it in without actually knowing the number on the network? And the deal is we simply double the backup time every single time. And then now we can approach the number of nodes on the network. We won't be exactly, right? So it will be at 100, if there's 100 on the network, right, the best that we can get is 0 through 127, right? But we might get lucky while we're scaling up and get the 0 between 63. And it works. But we can scale up and scale down now. So this is the idea of persistence. And the algorithm we just explained is binary exponential backoff. So binary, since we're just taking an exponent of 2 and then backing off that amount of time.
Why is it 1 over 2 to the n?
It's 1 over 2 to the n because this should be the probability of being next in line pi. It's 1 over 2 to the n to be the probability of, hey, I'm next, is what we're likely to achieve. And we achieve that by taking this number of frames, a random number in this number of frames to make this number a reality. So that is classic Ethernet. That's exactly how classic Ethernet actually works. It is a one persistent CS MACD network with binary an exponential backoff.
So,
You don't have to remember that, but it's one persistent because upon collision, the guy that transmitted first gets to transmit again, right? And then we achieve continual persistence by having binary exponential backoff. It is carrier sense because we listen first, multiple access because this is a multiple access scheme with collision detection. We listen and send a jam signal.
I was going to ask if the computer remembers the offset, or does it have to calculate every time that there's a collision?
No, it would calculate in your algorithm. You would say you would remember for X number of seconds or something, right, before it scales down, right, and that would actually be an implementation, right. So that means that if you didn't follow the standard implementation, then some network cards might be better than others, right? Because if you're not playing fair, right, you can now transmit more often than others. Of course, we're going to send packets, let's take a look at what an Ethernet packet looks like. So the first thing in the packet is going to be what?
To address?
Huh?
The to address?
Well, it's really close. But think back to the physical layer.
Preamble?
Huh? Preamble. And what's the preamble?
10101011.
It could be a code, or it could be something from the physical layer, right? This is our framing that we talked about 2 weeks ago. Our preamble is our framing. So it could be a code, or it could be something in the physical layer, right? So if we have some weird number of signals that we can stick in the physical layer, then we might take one of those signals because we can't quite make the next bit out of it, and take one of those signals and make it the preamble. It could be anything, right? But it is a frame boundary. And then the next is what?
2.
Yes. This is 2 like as an email 2, which is called the destination address. And then? From. From as an email again, which is the source address. And then we're going to have a type. I'm not going to ask for that. And then what do we have?
Data.
Data. And then?
Checksum. Or
Huh?
CRC or whatever the ending.
So we're going to have a CRC. And it actually is a CRC. We're also going to have a little bit of padding in here, because we want to land on byte boundaries. In this case, we want to land in, the padding is 0 to 46, so we want to be able to extend to the next 4 byte, right? So there might be padding. And the padding is useless data, but we're doing that because we're reading in 4 bytes at a time. So let's take a look, right? This gets sent into the wire first. That is our framing. So we end up with framing, then destination address, source address, type, data, padding, and then the CRC. Right? And then the next packet would have a preamble again, framing. And now we can send packets across. Now notice this is a contention network. So this is classic Ethernet, which means that it's contended, which means that A, B, and C are all talking across the same medium. This is not like modern Ethernet. Any guesses on what the difference between modern Ethernet and classic Ethernet are? Well, so modern Ethernet can actually have hubs. But on the hub part of it, it becomes classic Ethernet style.
So simply a switcher higher, right?
Yeah, so one is because it's switched. So on this, we have a single wire, maybe even a coax wire, but we have a single transmission medium. And even if we wired this into a hub with twisted pair, it still acts as a single transmission medium. So imagine we had, let's go away from networks, right, and talk about 2 computers talking. And I wanted to make a contention-free network between these, right, where I never have to worry about talking over somebody. I make 2 lines, right? I make a line this way, and I make a line this way. Notice that A can never talk over B if I do this. Now, the problem happens when I add the 3rd computer in this network. So if I was going to make this network the very simple way, what do I have to do? We have to add more cards. And this is going to get out of hand really, really fast. Right? But modern Ethernet works like this. It is contention free. And we'll get to how that actually works when it's over one wire. It's actually over 2 wires. But classic Ethernet works like this because we're talking over the same medium. So let's take those ideas and actually move it. It makes more sense right now to move to wireless, because we're going to use wireless is always contended, right? Because of the problem with broadcasting at the same time. So let's make a wireless network with the ideas out of this, and we will actually today get all the way to Wi-Fi. And we'll probably get to modern Ethernet. So now, I have a very simple network. I'm going to put 4 of them in this time because it's going to lead to some issues. So we want to do, use some of the ideas, but in a CSMA CD network, remember carrier sense, being able to listen, and collision detection is being able to listen to collision. We can't do that. So notice in our previous network, when a collision actually happened, we can immediately stop broadcasting the moment we hear the jam signal. We can just stop. But in a wireless network, because you can't hear a jam signal, or any other signal for that matter, while you're transmitting, then we have the problem, if you look at like a time diagram for wired versus wireless, right? We send 2 packets, even though they were supposed to be this long, right? We get the jam signal and we can stop transmitting. If we have the packet size of the same length in wireless, all of this time is lost. However big that packet is completely lost. Right? And it's actually lost for the length of both packets together, wherever the overlap happened to be. Because if A starts transmitting and the packet is going across air in this case, and then D starts transmitting, right? It's the length all the way from A to D and back. But it's also not only that, it's actually the length of the packets. So if the packet from D is actually longer than the length of the network, you lose all of that. Right? So that's going to make it inefficient. We also have some other issues going on. So what if A wants to talk to B and C wants to talk to B, but A and C are not in each other's range? So remember at the beginning of the class, I said there's some problems with wireless, and that if we look at like wireless antennas, where this is the antennas for A, B, C, and D, right? Our transmission has exponential backup. Or not exponential backup, exponential drop. So our transmissions look like this. So if A, B, C, and D are here, and their transmissions look like this, right? Then if A is talking to B, and C is talking to B, this doesn't exist. They cannot hear each other even if they were listening, even if it was possible. The problem with this is that the signal at B is overlapped, and A couldn't tell that it did it, neither could C. B is affected, but you can't tell. And that's because our radio range, it doesn't extend from A to C. We also have another problem. If B wants to talk to A and C wants to talk to D. So C is going to talk to D and B is going to talk to A. The problem is because these are in radio range, C and B can actually overlap each other. And we need to be able to fix that. It's actually not a problem to talk, but in our algorithm we need to compensate for that. It's not a problem to talk because if they were talking at the same time, B probably didn't even hear C talk, and C didn't hear B talk because they were talking at the same time, right? But we need in our algorithm to compensate for that. So let's take a possible solution to this. This is called MACA, multiple access collision avoidance. And we'll use that as a motivator for Wi-Fi. And our algorithm is this. So we've talked a little about this. So if a sender wants to send, it sends out a request to send. For the guys that are in the military, right, this is a seizing the air. So when I was a police officer, it would be 1 out of 61. That is my request to send. And then I would get a clear to send from dispatch that would say 1 out of 61, go ahead. And then we would talk. Because we're humans, right, we can kind of figure out when the conversation is over. So let's come up with an algorithm that looks something like that. So we're going to send an RTS, request to send. And then we're going to do a clear to send with the data size. So there's still possible to have collisions in this because A could send a request to send at the same time that C sent a request to send both to B. Right? So we haven't fixed collisions, but notice that in this we can make request to sends and clear to sends very, very small. And if we make them very, very small, we fix this problem. Right? Because now our collisions are going to be tiny packets. And that way, once the error is seized, everybody that hears the clear to send just remains silent for that time. Because when you're sending a packet size or frame size in your clear to send, everybody knows how long it takes for that to send. Haven't actually built in like variable bandwidths yet. So let's just say we have fixed bandwidth. We're not building in variable bandwidth. And so since the size comes around with the clear to send, then now you know exactly how long it takes to send that data, right? And then you do the same as you would with classic Ethernet, right? You do binary exponential backoff to do the next packet because you're putting an artificial boundary again and we want some gap in there. So let's take a look at what that looks like. In our first scenario, A was going to talk to B, but A is too far away for C to hear, and vice versa. So A sends a request to send to B. C does not hear it. C is too far away. And then B sends a clear to send. Back. Of course, B is close enough for C to hear. So C hears the clear to send. And now, this is important why the size is in clear to send and not request to send. Right? There might be an actual size in request to send, and then clear to send is acknowledging that size. But you have to send the size here because C needs to stay quiet for that amount of time. It never heard the RTS. And then it stays quiet. Remember, if it's a collision in this point, then we do something akin to classic Ethernet on doing backoffs until we get a real clear send. Let's take a look at the other one. So remember the other one, B wants to talk to A and C wants to talk to D. So B wants to talk to A, sends RTS. C wants to talk to D, sends RTS. Of course, B hears that, and vice versa. Possibly, B might hear or C might hear the beginnings of it, right? Not likely, because we're checking the air first, we're listening, right? So B actually won't hear anything, C won't hear anything. I guess it would be possible to hear the tail end of something, right? You'd be able, because there's some delay between these two. But regardless, there is no clear packet that makes it to either one. They don't hear anything. And then A sends the clear to send. And D here sends the clear to send. And then both communications can happen at the same time. Even though B and C are overlapping each other, and if there was some guy trying to listen right here in between, it would be completely nonsensical because there would be overlapping communications anywhere in here in between B and C. Because the signal from C is weakening so much that is just in the noise by the time it reaches A, then they can both send at the same time, even though they're overlapping near themselves. So let's modify that a little bit. So this is a wireless mesh network, right? So Wi-Fi is not a wireless mesh network, at least not in concept. It ends up that all the Wi-Fi signals get overlapped on each other, but most of the time you are talking to an access point, right? While there is ad hoc between two computers, most of the time you're talking to an access point when we're talking about Wi-Fi. So we're going to have to make a few changes to this, because most of the time we're not talking directly to anything other than the access point. So let's have A, B, and C. We're going to talk to the access point. We're going to do it in a time diagram. And let's say A jumps on. We're at some point in the network. Let's just start with A talking. And we're talking to the access point, let's just call that D. Everybody's going to talk to D. So what we're going to do is we're going to start sending our packet across. And then D is going to ACK. Now we haven't talked about this. In classic Ethernet, there is no acknowledgments. It has 0x. So if the CRC fails, then there's some error in the network, Ethernet does nothing. If that is the case, how do we fix errors?
Higher level protocols.
We let higher level protocols deal with it. Remember, reliability exists everywhere in the stack. And so in Ethernet, because it's pretty darn reliable, we just say, hey, the errors are far and few between, so we'll let some other protocol fix it as it gets up. Right? So we'll let the network protocol fix it. And if that doesn't work, then we'll let the transport protocol fix it. Right? So in this one though, because in wireless, errors are not far and few between. They are abundant. And because they're abundant, we don't want to let the higher level protocols, for efficiency, we don't want to let the higher level protocols have to fix all of the errors. Right? There still might be errors that get through, right? But we're going to try to weed out most of those as much as possible. So we're going to send data, and then we're going to get an acknowledgement of our data. The acknowledgement of the data also gives us a clear boundary for other guys to send. But we run into the same problems, right? We now have this artificial boundary. And if B and C try to send, by the way, while Wi-Fi does support RTS and CTS, so request to send and clear to send, it doesn't usually use them. So this is somewhat like a blend between the request and NOC and the Ethernet. We're going to try to blend these two networks together and try to use it. So what happens is if B wants to start sending here, right, it has to wait because it can hear A transmitting. If C wants to send here, it has to wait. But they can't just wait on this artificial boundary because we run into the exact same problems that we ran into with classic Ethernet. So what do we do? What do we do in classic Ethernet? Huh? Yes. We do exponential backup. Except for we can't hear collisions. So remember last time we scaled in by the number of collisions that we heard. Right? So now we can only infer collisions, right? Which is a much more arduous task. Right? So what we're going to do, and we would also like it to be more probable to not have a collision than to have a collision. Much more probable. In Ethernet, we didn't really care, remember? So we started out with 2, then we went to 4, then we went to 8, right? So that is collision, 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 collision. But because collisions weren't very arduous, because we can slim that down with collision detection, right? What we would rather now is try to avoid them at all costs, but use the same idea of random backoff. So what we do is we pick a random backoff, hoping that it will not collide. So we pick a bigger one, right? So let's say B picks a random backoff of 6 and C picks a random backoff of 3 frame sizes. So we're not starting out with 0 or 1 this time, right? Because we don't want a collision to happen. So at this artificial boundary, we now wait 3. And B starts waiting 6. These are the same size for a reason, right? Because C will start transmitting here. So what does B do now? Do we pick a random back off again? We want it to be fair. So B could be unlucky and pick a number of bad random back off numbers. So I think I had mentioned this in a previous class. What we do is he keeps the same random back off, right? But he's already spent 3 of them. So this time his random back off would be 3. Because he already waited once, and he waited 3, and he had picked 6, so he has to wait 3 more. And then we'll get data. If there's a collision, then we increase the back off, right? Pick numbers, but you pick the one back off that you had, and so long everything is going smoothly and things are transmitting, your back off completely is decremented. However long that you waited the network idle. So it's not this time with the data and the acknowledgement that you're waiting, this is network idle time. So if the network is idle for however long, you subtract that from your back off. And you send. Now, the reason that we do this is because before, when we had clear to send had to actually have a size. But some network, depending on where the location and the alignment of the planets or however else what is going on with, you just happen to have a really good signal, your computer has a better bandwidth opportunity than the guy next door. Or when we talked previously in the class, the guy 3 seats over from you. So you get to transmit at 54 megabits per second, he gets to transmit at 6 because of reflection or whatever else is going on in the physical medium. So if I do a clear to send with a size, I no longer can determine what that size is in the amount of time it takes to put on the network, right? So we would like to avoid that. And so we do that with this. So if B gets to send at 54 megabits per second and C gets to send at 6 megabits per second, right, this still becomes fair. And it becomes predictable. We're no longer relying on size. We have a random back off time, we decrement the back off time so it becomes fair. That way B doesn't have a long streak of bad picks, right? B, the more times B is, even if you had a really bad pick the first time, the more cycles that go through, if you had 100 computers or whatever communicating on this network, then this is always decremented. So the probability of B being next becomes higher and higher and higher and higher, right? Because eventually it will get decremented to 0 and he will transmit on the boundary. And he will either get to transmit or there will be a collision. Of course, this makes our Wi-Fi makes our packets a little weird. Why would our packets be weird in Wi-Fi versus a regular network?
Because we don't know delays necessarily.
So the big weirdness is that there are 3 addresses in a Wi-Fi packet. So in a Wi-Fi packet we have frame control and duration. And then what do we have after that? Destination, this is our 2, right? Then we have source. Then we have AP addresses. sequence number, data, and this is 0 to 2,312. And the check sequence. Checksum. It's actually a CRC for Wi-Fi.
So does the packet size remain the same no matter how much data you put in that data section?
No, no. Remember, because we have this variable length network, right? We are now engineering towards that variable length. Where before we picked, hey, we have a minimum packet size, right, a maximum packet size on this network because we engineer to 100 meters in most cases. Now we don't have that, right? Feasibly, we could have Wi-Fi that is, you know, with a big microwave antenna talking a mile away, right? And so or it could be from your computer to his, or very realistically, your phone to his phone when they're sitting next to each other, when you're transferring a contact or something over AirDrop. AirDrop works over Bluetooth and Wi-Fi, by the way. So both of which are wireless protocols. So AirDrop, if you don't know, AirDrop uses the 5 gigahertz of 802.11n, the 5 gigahertz portion, because the N gets to use both, and it uses the 5 gigahertz portion to be able to transfer data in a separate band. And it uses Bluetooth as the control channel for that. And since we're now at a link layer protocol, not an IP layer protocol, you don't need IP addresses, nothing, right? Bluetooth handles all the control data. And that's it. That's Wi-Fi. Some other details for Wi-Fi, which are somewhat not really important, right? It uses 20 megahertz or 40 megahertz channels in 20 or 40 megahertz channels in 2.4 or 5 gigahertz as the baseband. And so if you go to like your Homer problem, right, there's like 5 gigahertz and you have 20 megahertz channels inside of there so that you can, you know, if you ever worked with an access point, right, you can pick channels 1 through 11, I think, right? And some of those interfere with each other because they are harmonics of that 20 megahertz. And that's Wi-Fi. So modern Ethernet is this situation. We have 2 wires, one to talk and one to listen. We plug those into switches, right? We plug those into switches, but remember there's 2 wires, right? So commonly we'll make a switch, if we blow a switch out, we will make like, because there's 2 wires, we'll make it look like this. Right, where these are actually the same ports, but they represent different wires. Right, that way we can say, hey, we're going to talk, you know, go in this port, out that port, whatever. But where this port and this port, they're actually the same port, but this is the input side of the switch, and this is output. Because there's 2 wires. Now this is different than a hub, though there can be hubs in here. A hub is a contention network. So a hub, if we were to draw the same diagram, looks more like this. where you literally go in and you could literally think of it as you're twisting the wires together. So that means that if A was talking to C, it goes into the hub, goes down to where it's all wired together, and then out to everybody. Because it's a contention-based network. A switch is something entirely different. A switch, inside of the switch, very simple in this case. There's a fabric. And the switch has logic inside of it to say, hey, there's something that came into this input. So we have network cards A, B, and C, and we have ports 1, 2, and 3, and this is still 1, 2, and 3. And inside here we have a fabric, and there's logic inside here, and it reads the destination address. This is not yet an IP address, right? These are MAC addresses. And it reads the destination address and maps it to a port. So imagine we have a table. And we have computers over here, or network cards, however you want to think about it, and then ports over here. And so in this case, where this is 1, 2, and 3, right? So then we would have computer A is port 1, computer B is port 2, and computer C is port 3. And then there's logic in here so that a packet going in port 1 can, if A is talking to C, there's logic that goes through here to say, hey, pick this path to port 3. And that is a switched fabric, which is why it's called a switch. Now the question is we've never filled this table out, right? Everybody in here has dealt with modern Ethernet. You plug it in and it works. So how on earth do we figure out the port mapping? This is now we're out. We might never revisit other than we'll do some bandwidth delay products on picking packet sizes and stuff like that, right? But now we're into the computer science part of it, right? How do we detect, we plug all these things into the switch, how do we detect that computer A is on port 1 and computer C is on port 3 to make our tables?
ARP.
Huh?
ARP.
Actually, ARP is for IP resolution, right? We need to be able to figure out port resolution to max first. How do we go about doing that?
Wait till someone transmits?
Yes. What happens if somebody transmits? If A wants to talk to C, A says, it has no idea about the switch, right? It just communicates, right? It says, I send out this Ethernet packet, right? And now we're in a modern Ethernet. I don't have to worry about collisions, nothing. I jam that thing on the wire, right? It goes to the switch. The switch does what? It sends it to everybody. So the switch gets turned on. It actually knows, I guess I can leave this here. It knows that it's its own switch. It knows that it has port 1, 2, and 3. The switch gets turned on. A sends a packet. So the packet comes in here to the port, the input port, and it looks at the table, and the table is blank because it just got turned on. But it learns something from that packet. It learns that A is on port 1. It learns that A is on port 1 because the source address is in the packet. Right? So it can write this. And then it does exactly what he said. It sends it out to everyone. So in this case, it probably doesn't send it back to A, right? Because it learned. But so ostensibly you say, hey, write the table and then send it out to everybody, right? And so then it goes out 2 and out 3. So now B receives a packet that it wasn't meant for him. So B just disregards it. The address isn't correct. C receives a packet that was meant for her. So C says, oh, great, right? And then communication starts, right? It's usually not one way, is communication starts. So C sends a packet back. The switch encounters that packet and learns that C is on port 3. And then doesn't send it back to everybody because A is now in the table, right? And so now you're no longer spamming packets out to the network, right? There is a communication that's going through here and back and forth. Contention-free communication, right? You just don't have to listen, don't do anything, jam it on the network. So, and then the same thing would happen for B, right? If somebody sent something to B or B sent somebody something, then, like let's say A sends to B, right? Well, if A sends to B, then it can actually deduce at this point that it's probably 2, but you don't want to rely on that because it might be, B might not be on the network, right? You wait for the response, right? And but it might, depending on your algorithm, it might only send it to because that's the only possible place it could be, right? But those are in the details of the algorithm. And then B responds, and then B gets learned that it's in 2. We have a problem though. What is that? We do have a problem. So remember, this is a contention-free network, right? Which means that you just jam stuff on your wire. You don't listen, you don't do anything, nothing. There is another problem.
What if 2 people want to talk to the same person?
2 people or more want to talk to the same person. Let's say we have a network of A through J, and J happens to be really popular, and A, B, C, D, E, F, G, and H are all trying to talk to him. So they're all talking at line speed. You're jamming packets on the network at line speed. So if this is a 100 megabit per second network or a gigabit per second network, you're literally putting on that fast, right? So now J has 10 gigabits worth of line speed going into a 1 gigabit pipe. So how do we fix that? We fix that by building buffers. So you can think of it however you want. I put an input buffer and an output buffer, but it's really just a set of aside memory, right, where the packets are queued up in order. What happens when the queue gets full?
Drop packets.
We just drop packets. And we'll talk about dropping packets a lot, actually, when we get into transport, or even IP. Because that's dropping packets actually becomes a mechanism to actually for A, B, C, D, E, F, G that are talking to J to throttle back on sending the data, right? But that's handled in the transport protocol. So in the transport layer. So, but we would have some amount of memory so that we know that there will be at certain points where this thing is talking. This memory is, by the way, from a like implementation point of view, this memory is super expensive because it has to be super fast, right? Because it has to work at the line speed of this switch on however fast data is being passed across. So it's not like you can just put a gig of memory and just be okay with it. So let's take a look at one more thing. This actually works with more than one switch. What if we had two switches? Let's call them X and Y. So we have X and Y switches with A, B, C, and D, E, and F. We're connected to ports 1, 2, and 3. Like this. Does our little algorithm to do port mapping still work? Yeah, it actually does. A wants to talk to F. The whole network was just brought up. A wants to talk to F. What happens? A goes in port 1, right? So we learned that A is in port 1. It spams it out everywhere else. So the packet goes to B, goes to C, goes through port 4, and into port 1 on switch Y. Y learns that what? It learns that A is on port 1. It's port 1. Right? And then it goes out to D, E, and F. F gets the packet and returns it, right? And so we learn that F is on port 4. It goes back out here, and A, we already know A is on port 1, so that goes back into here, and then it just goes out, right? And now we have a communication. We know the path back and forward from A to F, right? So B sends something to E. B goes in port 2. We learn that B is on port 2. Goes through here, goes into switch 1. We learn that B is here on port 1 also. Right, and then it goes to E. E returns the information, so we learn that E is on port 3, and it goes back out, and then we learn, so F is on port 4 here, we learn E is on port 4 also, right? So the whole thing, it works. We can connect multiple switches. That's not an issue. There was some, who remembers back in the old days, that when you connected switches, you had to have crossover cables. Right? Why did you have to have crossover cables?
Because it would conflict.
Yeah, because there was a line to communicate and there was a line to listen, and you needed to flop those over if it was between two switches. Right? Otherwise, the talking and listening line would be hit on, and the other line would be dead. Right? It would be so you flopped it over. Now we have just detect. Right? But this whole port mapping works. Works for Ethernet. It does not work if we do this. Does not work if we do that. And we will talk about that in next class.
said you were doing